it's gone. It's done. Yeah, we always forget to do the enable auto start thing.
Yeah, we need to automate this setup somehow, because there's always like one button that you forget to click.
Yeah, it's not good. Anyway, thanks so much, and everyone, and especially thanks Sahar and Mario for taking the time to present their work here at UCL. It's a great pleasure. I'm going to introduce Sahar, who I believe is going to give the full seminar, right? So Mario is here for support. Right, so Sahar is a PhD candidate at CISPA in Saarbrücken in Germany. It's advised by Mario, and she's done a lot of work sort of at the intersection of natural language processing, computer vision, and machine learning and security. And she overall studies vulnerabilities, limitations, and malicious use of machine learning and how to defend against them. And so today she's going to talk about multi-modal fact-checking, out-of-context images, and how to catch them. So without further ado, Sahar, thank you so much. Take it away. Thanks.
Thank you so much, Mariano, for the very nice introduction. And I'm so glad to be here. I would like to thank everyone for attending and for your time. So today, as Mariano said, I'll be mainly talking about multimodal fact-checking, and I will introduce our recent work, basically how to detect and catch out-of-context images. So as I go on in the presentation, please feel free to interrupt me anytime if you want to ask any questions in the middle. Okay, so, okay, sorry, it seems my presentation is stuck. Okay, no, it's okay. Okay, so I first would like to start with an overview of the topics that I'll be talking about today. So I have been working on developing machine learning-based solutions against misinformation, specifically against these two types. The first one is human-written misinformation. So in here, adversaries or malicious actors can create or craft certain claims that are not entirely true. They might want to propagate and spread them. So this process is mainly human designed, but as I will also discuss, it can be assisted by AI models. The second category is machine-generated misinformation, or possibly deepfakes, as we all might know them. And in here, malicious actors can misuse generative technologies, such as GANs or large-scale language models, in order to generate and propagate fake machine-generated content. Okay, so I'll first start with this part, the human-written misinformation. So in recent years, there has been a lot of focus on studying misinformation, specifically textual fake claims. And there has been a lot of wonderful work on studying how they propagate, their characteristics, and how to detect them. So one detection line, for example, is studying the linguistic cues that could separate these fake claims from actual real news. So for example, they might have lower quality, they might be underwritten, they might have specific biases, such as they might try to be more provocative, for example. However, one obvious drawback of this detection line is that it's not very sustainable against the evolving natures of adversaries or possibly changes in style. And therefore, currently, there is more focus on automating fact-checking as a solution to defend against misinformation. And in here, the task is given a certain claim. The task would be to retrieve relevant evidence and then automatically try to detect the stance or the credibility of the claim with respect to the retrieved evidence. However, there is generally less focus on multimodal claims. And in here, in multimodal claims, the claim consists of both an image and a caption. And also, there is less focus on automating fact-checking for multimodal claims, which would be the topic of my talk today. So this will move us to our paper here. So our paper was titled Open Domain Content-Based Multimodal Fact-Checking of Out-of-Context Images via Online Resources. So it's a bit long title and mouthful, so I'll not be saying again. But I'm so glad to share that this work has been just accepted at the CVPR this year. And it's a joint work with Rakibur Hassan and my advisor, Mario Fritz. Okay, so at least from the title, it seems that this work is about out-of-context images. So I first would like to define or introduce what out-of-context images are. So let's assume that we have a scenario where the adversary is starting from a narrative or a certain textual claim that they want to propagate and promote. So before they do this, they first pair it with an image. This image could be a real image that has appeared before in a real context, but in an earlier or a different context. The motivation behind creating this pairing is to possibly add more credibility or visibility to the claim and possibly engage users, because recent work has shown that people might tend to believe or engage with certain stories if it were accompanied by images. However, this pairing is falsified because the image actually belongs to a different context. And by creating this pairing, the adversary is using this image in an out-of-context way or repurposing it in order to support a certain narrative. The dangers of this type of misinformation is that it's so easy to create because it doesn't require sophisticated technical knowledge. And at the same time, since the image used here is a real image, these created examples might be very convincing. Furthermore, recent work has shown that the task of retrieving a relevant image given a query or a caption can be automated through the use of AI models such as OpenAI Clip. This has a good part to it because now starting from real news images, we can automatically construct and create out-of-context data sets. So in this work, they have started from a larger scale data set of real news images and real news captions, and they used Clip and other trained machine learning models in order to in a careful way, mismatch real news images with real news captions in order to mimic the creation of these out-of-context images. So now, starting from a naturally occurring real data set, we can automatically have out-of-context data set. This would enable the detection research of this type of threat. And it also doesn't require expensive human labeling, and it also can make us obtain very large-scale data sets that are hard to obtain due to the scarcity of the actual out-of-context images. However, it has also a bad part to it because now it shows that adversaries can actually misuse these technologies and these models to make it so much easier for them to create out-of-context images at scale and automatically. So before I move on, I would like to show some examples here. This was from the original news clippings paper or the original benchmark. And in here, they show real world examples of out-of-context images. So for example, here in this image, this is a real image, and the wrong claim says that these are US senators. However, the actual image belonging to from the UK. And this is also another example. So these are refugees, and the claim says that it's a refugee situation at the US, but the actual image has happened in the borders of Austria and Germany. And also we have here other two examples. So this is not the person that the caption claims it to be, and it's also a very different context. And in this last example, we have here an image of a person, so it is the same person that the caption claims it to be. However, it's a totally different event or a different context. And the paper takes some inspirations from these real-world examples in order to mimic the creation of out-of-context images that misrepresent where the event happened, or people in the image, or the context of the image. So as we see, these examples might be really hard to verify if you don't know the real event, and they might require external knowledge in order to be able to verify them. And this would be the motivation behind our work. So we want to integrate fact-checking with the task of how to detect out-of-context images. The motivation behind that is that the original benchmark or the original paper has shown that the detection performance of both machines and humans is very limited, and the task is actually very challenging, even given the constructed synthetic data set that they propose. And therefore, we propose here to, given the query image and the query caption, we propose to leverage external knowledge that we will, or external evidence that we will get via online resources or via internet search. And based on these external items that we will find and external evidence, we would like to verify the pairing of the image and caption in order to detect if this is a true or falsified pair. So let's take this example here from the dataset. So we have here an image and a caption. The caption mentions that this is David Cameron and he is speaking in some event. So we might know from our previous information that this is David Cameron, and also a machine learning model that's trained on the facial recognition task might also know that this is David Cameron. However, we are not so sure about the context, and this is what we are trying to verify using the external information. So in our case here, we would take the image and the captions as queries in order to perform internet search. And based on the search items, we would like to verify if this context or event is true or not. So we first set some requirements for our retrieval and fact verification task. The first thing is that we want to have an open domain setup, meaning that we will not be restricting the evidence to come from a certain website or a certain source that we know is relevant to the query. And at the same time, we will not be pre-processing the evidence item or maybe labeling the relevant evidence items before giving it to the model. The motivation of that is that we want to have, as close as possible, a real word setup where a person might use the internet freely in order to find all sources of information, and also not all sources that we will find out there is relevant to our queries. And the second thing is that since now we have a multimodal task, we have an image and a caption, we want to use the content of both these modalities in order to find evidence, in order to verify the claim. So we do the fact verification through something we propose, we call multimodal cycle consistency. So to explain that in a nutshell, we will be starting from the image and we will use it as a query to perform an inverse image search. This means that we will find the occurrences of that image on the web. And from these pages that we will get, we will crawl or extract text snippets such as captions or titles, and these snippets will work as textual evidence. And then we will compare this textual evidence that we got with the query caption that was originally paired with that image in the test example. We'll also do it the other way around, is starting from the caption, we will find some images, and these images will form visual evidence that we will compare against this query image. So the intuition here is that if this was a true pairing, then we would expect to see some consistency here between the evidence that we will find and the other modality that was paired with the image here, for example. However, if this was a falsified pairing, then we might see some discrepancy here, and the objective would be to detect whether we have a consistency or discrepancy. So let's see what the evidence would look like for this example. So please don't get discouraged by the big image. I will try to walk you through it. So as I said, we use the image to search for textual evidence. And in our case here, in our case here, the textual evidence can be divided into two main parts. The first part are the named entities, and these are short sentences or named entities that are returned by the search API. And currently here we use the Google Inverse Search API, and these are the named entities that were mostly associated with that image. And at the same time, we have these textual snippets that we crawled from the web pages. And as I said, we want to compare the consistency with the query caption, and we do it through this text-text consistency part of our model. So when looking at the textual evidence here, we can see that it mentions David Cameron. We might already know that because we know that this is David Cameron in the image. However, it here mentions that he is speaking in some event in Jamaica, and this is probably different or contradicting with what the caption says. And we hope here through this text-text consistency part is to be able to automatically detect this kind of discrepancy. So the yellow highlighted parts that I'm showing here, these are the items, the evidence items that the model highly attended to. So we can see here that the model highly attended to some overlap with the query caption because since it's an overlap, so it seems like it might be relevant to the query. But at the same time, it also attended to some contradiction or contradicting or conflicting information, such as the location that is different from what the query says. So as I will mention later, we want to have an inspectable system as much as possible, and therefore having this attention signal that sort of tells us what were the most relevant items according to the model is probably very helpful if we want to have a humans in the loop setup or an assistive fact-checking setup where a person is using the model in order to help them do the fact-checking task. Okay, so that was for this first branch. We also do it the other way around, is that we start from the caption, we search for images, and these are a snippet or a subset of the visual evidence that we got. And again, we see the same person, and we already know that, but we want to be able, through this image-image consistency part, is to want to be able to say that this is probably different context because it's a different scene or a different place. And finally, the original benchmark didn't consider external evidence. They studied the image caption consistency. And therefore, we integrate also that part in our full pipeline in order to detect any possible inconsistencies between the paired image and caption. And finally, we hope to aggregate all these parts and the information and output from the 3 submodules and from all evidence items. And for that example, the model predicted it correctly as a falsified, which is the ground truth. Okay, so this was a summary of the overview of the method, how we collect the evidence, and how we plan to reason against it. So now I will give slightly more details about the design of the model. Okay, so as I said previously in the previous slide, we have 3 components in the model. So we want to be able to detect the consistency of the image caption pairing, and therefore we call the model consistency checking network, or CCN in short. And we have here 3 components: the visual reasoning and the textual reasoning and the clip component. So I will start with the clip. So the clip component is to measure the consistency of the image and the caption themselves without any external knowledge. And in here, clip is an open AI model that was pre-trained. It's a multimodal model that was pre-trained with the objective of matching text or small snippets of captions with images. And therefore, its pre-training objective is very similar intuitively to the task that we want to have. And we follow the original news clipping paper in that. They fine-tune clip on the task of predicting whether the caption matches the image or not. And we also utilize the fine-tuned clip in our full pipeline. So moving to our main contributions about the visual reasoning and textual reasoning. As the main motivation, the visual reasoning tries to find the consistency or the similarity between the query image and the visual evidence. And again, as a reminder, we got the visual evidence when we searched with the caption. So the main takeaways here is that we want first to use different strong representations of the images, and therefore for the query images and the visual evidence images, and therefore we utilize here 2 pre-trained networks. So the first one is a ResNet model trained on ImageNet, and also to encourage the model to be more aware to differences in scenes and places, we utilize a ResNet model that was trained on the scene classification task. And also to have more fine-grained reasoning about the regions in overlap or the similarity between the query and the evidence, we here compute labels of regions in each image, and we compute a feature that is the count of the overlapping of labels of regions between the query and each visual evidence item. And then we concatenate that with the evidence features. And finally, as I said, since we have an automated task and automated fact retrieval system that we don't filter out the evidence, so we might have a lot of evidence items that are not really related to the query at all. And therefore, we want to allow the model to be able to selectively reason against the relevant part only. And therefore, we utilize here memory networks. So we use memory networks to store the evidence items for each representation for the ResNet and ImageNet and the scenes. And the query to the memory here would be the query image. And also, as I said, utilizing memory networks would allow us to have some sort of attention signal that we can later use as sort of inspectability method. So that was the takeaways of the visual reasoning. The textual reasoning also has very similar motivation and design. So again, we want to compare the similarity of the query caption against the textual evidence, which we got while searching with the image. And if you remember, we had two types of textual evidence. So we first had the entities. These are small text sentences that are returned by the search APIs. And these are the full sentences or the captions that we crawled or extracted from the web pages. And we also here have similar ideas that we want to have strong representations of the language. And therefore, in this sentence embedding module, we utilize pre-trained contextualized embeddings like BERT, or we also experimented with transformer models that were trained on the sentence similarity task. These models generally might contain a lot of word knowledge, and this would be helpful in our task, and therefore we utilize these pre-trained contextualized embeddings in order to get strong representations. And also to encourage the model to be more aware to the named entities overlap, we also compute here a binary feature that tells us if there is a named entity overlap between the query and each evidence items. And also finally, with the same motivation of selectively reasoning against the most important parts, we utilize here a memory network for each type of evidence, the entities and the captions. And again, the memory networks will give us a sort of attention signal that would be helpful for us. And I will talk about this in the experimental evaluation. And finally, we here aggregate or concatenate the output of each memory in the visual reasoning and textual reasoning and concatenate that with the clip output. And finally, the model is classified, is trained to classify whether the query image and the query caption, given the visual evidence and the textual evidence, whether these pairs are true or pristine or falsified. Okay. So that was the overview of the method. Now I would like to move to more cool parts about the experimental results. So currently I will show the most important results that we got. So for the first evaluation axis here, we wanted to evaluate how much gain in performance we can achieve when we utilize our evidence-based detection. And to do that, we compared to the main baseline that we used here was the clip-only baseline that was used in the original paper, and this model only used this baseline only used clip and didn't consider external knowledge. And we can see here that we actually achieved a significant increase in accuracy and in performance compared to the clip-only baseline. However, we also, since we don't have any evidence-based detection of our task, we also propose another rather simpler baseline here that also utilizes evidence. So in here, we take all evidence items and then we compute their representations and then we average these evidence items and perform a classification based on this average. This performed decently because it's higher than the clip-only baseline. However, it's also much lower compared to our full model. And our interpretation and takeaway from that is that simply considering evidence in a very naive way is not enough because the task is challenging even given the evidence, and therefore we need to have our other improvements like the representations design and also the memory networks in order to be able to do more fine-tuned reasoning or fine-grained reasoning, and also to be able to selectively attend to the most relevant items. Okay, so that was for the main quantitative results. We have, I'm showing here the best full model that we got, but for more detailed ablation studies, you're very welcome to check the paper. You can find more information about the effect of each component there. Okay, so the main other thing that I will talk about now are user studies. So we performed some user studies in order to answer some questions. So the first question that we had is, does the evidence that we got, does it really improve the human performance? So it seems like it improves the machine performance in detection, but is it also helpful for humans in order to identify mismatches? So what we did here is that we selected a sample of 100 pairs of images and captions, and we have shown them to users through Mechanical Turk, and then we asked users to decide whether these pairs are pristine or falsified, given the evidence. So we have also shown them the evidence that we retrieved. And we found here that compared to the similar study that was actually reported in the original paper, we achieve around 16 percentage point increase in human performance over the original study. And we also asked users what kind of information helped them in order to reach the final conclusion. And you can also find that in the paper. And in a lot of examples, users mentioned that the evidence was the most important part in their decision compared to only relying on the image caption pairing. So that was the first question. The second thing is that we wanted to see or evaluate, does the model really attend to the more useful evidence? Why is this important? Well, as I said, it could be important if we want to rely on the somehow use the model in a assistive fact-checking setup where we might use the attention that we got in order to inspect the most important evidence items, or we want to make it easier or faster without having to go through all the evidence items that were retrieved. And therefore, to do this, to evaluate this, we designed another user study. So using another 100 pairs that have enough evidence retrieved, we sorted the evidence according to the attention of the model. And then we perform two variants of this study. So in the first variant, we show users the highest attention, and the second one, we show them the lowest attention, and this was done by non-overlapping users. And we found here that the group that actually got the highest attention achieved a higher detection performance compared to the other group. And from that study, we might here have a suggestion that says that the attention item that we can, the attention signal that we can receive by the model might also be really correlated with how important or how useful users found the evidence. Okay, so I would like now to show you some examples. So I've already shown a falsified example. There are other examples in the paper that also show some some falsified examples that are different beyond only the location. So yeah, please feel free to also check that in the paper. But at this point, you might be wondering how the true or pristine examples might look like. We have already seen a falsified example. So these are some also pristine or true examples. And the cool observation here that we found is that we don't need to have an exact match of the image or exact match of the query in the textual and the visual evidence in order to reach a conclusion that this is a pristine example. So in here, these are a subset of the visual evidence that we got using this caption. And in here, this is again the highest attention image. And we can see that the model, for example, prioritized these two images because they are somehow similar of the scene of the query image compared to, for example, this image that might be from a different location or maybe different view. But these two images look, of course, look more similar to the query. And also for the textual evidence, we can find here that the model also sort of prioritize the caption that is more semantically similar. It has more overlap in the named entities, and also for the named entities, it also highly attended to things that are overlapping also with the query caption, like the name of the city, or maybe that is a Japanese, it is located in Japan, and so on. And also the consistency or the similarity, they don't have to be in the locations only. So for example, here we have a query caption that has a sentence, subset sentence that says soon to be Trump International Hotel we see here that the model also attended highly to this similar overlapping sentence here, which is not even an exact overlap. And also for the images, we can find that the model prioritized this image here because possibly because it's from the same scene. We can see here that we have these two flags in the background. This is in contrast with this image here that shows the same person, but in a different place or in a different context. And therefore, this is probably more similar to the query. Okay, so this was the main part of my presentation. So I would like to conclude with some recap or takeaways. So the first thing is that in this work, we propose the first benchmark for multimodal fact-checking for out-of-context images. And we do this by utilizing the information of both the image and the caption and performing the cycle consistency check. And we found that this approach really effective compared to not relying on external evidence. And we also scale to open domain setups. We might have a lot of noisy signals, and we don't rely on any supervision of relevance or any processing. And we found that the model could still attend to the highly relevant parts from the evidence. And finally, there are some pending directions that we probably would like to work on. So the first thing is currently we might need to examine the robustness of the model. So this could include the robustness to maybe the complex or hard examples, or maybe even to malicious attempts in order to introduce some poisoned example in the evidence, or maybe to introduce some contradiction or confliction or conflicting information between among the evidence. And the other direction is that currently we use this synthesized data set because it's more convenient and more large scale. And the original paper shows that it's somehow similar in spirit to actual real world examples of misinformation, but it could still be a nice, interesting direction to examine the performance against in the wild misinformation. So to see if a model that is trained on this synthesized data set, would it still be able to detect with the same model, would we still be able to detect some in the wild examples or not? Okay, so that was the first part and the first main part of my presentation, is human written misinformation. So here we say human written because the images are real, and also we don't assume that the captions are generated or manipulated. However, according to this categorization, we also have a machine generated type, which is the misinformation. Machine generated misinformation. And we also developed solutions against these. And our solutions are based on watermarking or fingerprinting. And we have done this for language and for GANs. And I will go very quickly into our two ideas here, just to explain the setup and the motivation. Okay, so I'll first go through the language watermarking solution. So this paper was published at OutofContext last year, and the title was Adversarial Watermarking Transformer. And in here, we propose a language watermarking to watermark input text. So the main motivation of using watermarking for language and also for GANs later, as I will talk about, is to move from passive to active defenses against deepfakes. So passive here means that we would be current defenses against deepfakes are attempting to perform a classification sort of between the fake distribution and the real distribution. However, as we all know, generative technologies are getting so much better, and therefore this gap between the two distributions might be getting narrower in the future, and therefore these passive defenses might not be very sustainable in the long run. And therefore, by watermarking, we propose to introduce active defenses, meaning that we want to introduce a traceable fingerprints or watermark in the generated media, such as language or images, in order to be able to trace the provenance and the origin of these generations. So in that work, we assumed the following scenario. So we would have a language model owner that is responsible for training a language model, and that owner might have some concerns about the misuse of their own technology, and therefore they responsibly and proactively introduce some watermarks in the output. And in that work, we assumed a black box API. And this is a realistic setup because currently we have models like GPT-3 that's only available through a black box API. So later, a malicious user might use this API in order to generate fake content at scale, such as entire articles. However, these generations now contain the watermark, and therefore news platforms can ideally cooperate with language model owners or some regulation entities in order to have a way to detect these watermarks through the watermark decoder. And if we are able to detect the watermarks that we know we have already inserted during training or after training, we can attribute these generations to that specific model and conclude that this is a machine-generated text. So the idea here is that we want to enable model owners and technology with a way to responsibly release the technology and possibly regulate the use of such AI models in order to avoid the risks. So currently, in that work, we assumed the black box access to the API, and therefore we relied on a post-processing watermarking. So for that here, we introduced AWT, and this is was the first end-to-end framework for watermarking text in a learned way without relying on rule-based substitutions or without having any pair training data. So that solution basically was that we would have a hidden network that is a sequence-to-sequence model that receives an input text and also receives an input message. And the goal here and the objective would be to produce an output text that's similar, preserving as much as possible the input, but at the same time, it should contain the message in a way, or should encode the message. And this is trained at the same time with a revealing network that takes the output and should produce the reconstructed message. After training, this revealing network or the message decoder can be used in isolation from the input in order to decode the watermark from some text that we don't need to have the embedding, so we just need to have the text itself. And as I said, we don't have any training, paired training here and training this model, and we relied only on optimizing these components or these losses, the reconstruction of the message and of the text. So there are, of course, a lot of evaluation requirements and requirements for the task. And in that work, we mainly set 3 requirements. The first thing is that we want to have high effectiveness, meaning that we want to preserve the quality of the output in order to still have a high utility of the black box API. And at the same time, we want to effectively decode the bit accuracy in order to have a successful encoding and decoding of the watermarks. And the second thing is secrecy. So currently, in order to have a subtle encoding that's sort of difficult for adversaries to infer whether the watermark exists in the text or not, we want the watermarks to be indistinguishable. And the last thing is we want to have some resilience against the automated removal attempts because it shouldn't be so easy for adversaries to remove the watermark, of course. So we took inspirations from these evaluation requirements in order to design our model. So the first thing, in order to preserve effectiveness, we try to preserve the quality of the output through minimizing the sentence embeddings between the input and output. And at the same time, we want to maximize the likelihood and the trained language model in order to produce correct output that doesn't have a lot of grammatical mistakes. And for secrecy, we utilize here adversary training, and we found that it's really effective to have more subtle encoding of the information without obvious marks or obvious signs. And for robustness, we studied a range of attacks that assumed random perturbations and also assumed more adaptive attacks. And we found here that already improving the effectiveness and the quality, and at the same time improving the secrecy, made it harder to remove the watermark without introducing big changes to the output text, and therefore it led to higher robustness. Okay, so I'll not be going into more details about the evaluation, just a sneak peek. So in that work, we compared AWT to some synonym substitution baseline that we proposed. And in here, these are based on fixed rule-based substitutions. And we found here that our solution achieved much better trade-off between the different evaluation axes. So for effectiveness, we achieved a higher bit accuracy, and higher semantic similarity between the input and output text, and also the automated classifiers that were trained to infer whether the watermark is there or not had close to random chance performance, and therefore we had higher secrecy. And for robustness, we also found that the performance of AWT is much more stable than the performance of the synonym substitution baseline under the same attack setup. Okay, so this was in brief what was this language watermarking about. So the idea of watermarking can also be extended to GANs, which what we did in this work here that was published last year in ICCB, and it was led by my colleagues Ning and Pat. So the same motivation here is that we want again to use watermarking to have active defenses, and we also had a similar envisioned scenario is that we would have again owner that would try to watermark the GAN, and then the different thing here is that we assumed either a black box or a white box threat model, so the model itself can still be released. However, when a malicious user is now using either the black box or the black box, the watermarks should be contained in the output. And finally, similarly, the news platforms should have a way now to cooperate with owners through some regulation entities in order to be able to detect the watermark. And if we can detect the watermark, we can attribute it to the specific GAN model that we know have this watermark. So you might be wondering, how can we do this for GANs? So it turned out that there is a really simple way to do it, and at the same time, it's really effective. So we did it, and that worked through watermarking the training data. So we found that if we actually watermark the training data without introducing any changes to the GAN, this will lead to a watermarked GAN, and this will lead to a watermark output. So in a nutshell here, what we do is that we first train a watermarking model to embed a random message into an image. And at the same time, this is trained with a decoder that should take the output image and try to reconstruct the message from it. And then after training, we fix these watermark of fingerprint encoder and decoder, and we use the encoder in order to encode a fixed message into all the training data of the GAN. This would result in a fingerprinted training data. Then we can use this training data to train the GAN model without making any changes, without assuming that we know the exact architecture of the GAN or any details about it. And it turned out that the surprising discovery is that if we actually use this GAN model as it is, we can see that we can actually detect the watermark from the generation. And therefore, the watermarks are transferred from the training data to the GAN and to the output without actually introducing any changes to the GAN training. Then we can, based on the fingerprint decoder, we can compare it to the watermark that we know we have already inserted into the training data, and then try to establish if there is a match between them or not. The properties in this solution is also very similar to the language watermarking that I talked about. So the transferability and the fidelity is related to the effectiveness of the watermarking. So this means that we should be able to decode the watermark from the output, and at the same time, we should keep the generation quality of the GAN in order to not affect the benign users. And we found here that through a range of data sets and GAN models, we can achieve a very high bit accuracy here. And at the same time, we can achieve minimal changes or insignificant drop in the quality of the generation images. And also similarly, we should have high accuracy. So we found here that trained classifiers that try to predict whether there is a watermark in the output or not achieve the close to random chance performance. And finally, again, similarly, we should have a high robustness against removal attempts. So we found here that we examined a wide range of perturbations to the image, and for each perturbation we also examined the relationship or the trade-off between the bit accuracy and the noise setup or the perturbation range that we add. And since we assume a white box scenario, we also examined some model perturbation, like changing the weights or adding noise or perturbing the weights. And we found here that through this analysis is that we can achieve a relatively good trade-off. So removing the watermark in a way to make it not very usable would also mean that we would degrade the quality of the output or highly degrade the quality of the model in case of the image perturbation or the model perturbation. Okay, so the takeaways from these two works that I talked about is that the motivation of them is quite similar, is that we want to move towards active defenses against AI abuse instead of relying on passive defenses that might not be very sustainable in the future. And we hope that this would open some new research directions on the responsible release and the regulation of AI generation technologies in order to actively and proactively prevent such misuse and such threats and dangers of AI. Okay, so that was the conclusion of my presentation about my current work in misinformation. And thank you so much for your time. Sorry if I took so much time, and I'm be happy to take your questions.
Great, thank you very much, Sahar. Maybe we can stop the recording. I don't think I can.
Yeah, I'll do 1 second.